Part 3. This should be pretty short. There's only a couple slides to go over, but I wanted to have enough time to discuss it. So instead of rushing it at the end of the last one, I decided to give myself a little more time. A couple more items. Number one is something called saltwater intrusion. Now, this is not what most people think of when they think of pollution, but it is caused by human activity, and it has to do with how the groundwater system looks near the shore. So here we have a side view that we saw when we were looking at groundwater resources. You've got the water table. The arrows show groundwater flow. You'll notice that salt water occurs below the fresh water, and that's because salt water is more dense than fresh water. If you were to drill a well here in Illinois, if you go deep enough, you will hit salt water. So a lot of the groundwater, when you get really deep, is not potable. It's not drinkable because of the high salt content. And that has to do with the fact that the water's flowing through rocks, and it can pick up materials that then become dissolved in the water. There are other reasons for that as well. But when you get near the coast, that saltwater layer is connected to the ocean. And you can see on this diagram here that there is an interface zone where the water is kind of salty and kind of fresh. So this is kind of the way the system normally works, with the fresh water floating on top of the salt water. If you start to pump the fresh water, remember the cone of depression that we talked about, created due to low pressure around the wellhead. Well, that low pressure also affects the deeper groundwater. It can actually start to pull salt water up toward the well. And so saltwater intrusion occurs when you start to overpump these wells, when you pull the fresh water out faster than nature can replace it, and you end up with a polluted well and polluted groundwater because the salt has now moved into the area. Now you might think, hey, if we stop pumping the well, things will go back to normal. And they might, but on the other hand, some of that salt can then be left behind in the earth materials that you were pumping the water out of. So the salt does not necessarily just go away, and it certainly doesn't go away quickly. So when you're near the coast, one of the things that can be done is, if you need more water, instead of pumping so hard that the salt water intrudes, you can just lay your pipe right in the ocean and pump that out, but that water would have to be desalinized, or the salt removed. The other alternative is to get a water source that is away from the coast. New York City, for example, has lakes up in the Adirondack Mountains that supply it with fresh water, and cities along the West Coast very often rely on water sources that are lakes up in the mountain to the east of those cities. So, next topic to just mention is would be water quality standards. So how do we define what is clean? Well, water quality standards are set by the government, and it's a combination of things that go into it. Science is right there at the top. Obviously, we don't want people to get sick, but there are also economic considerations. There are technological considerations. Sometimes there are contaminants that we just can't remove. There are ethical considerations, and politics gets involved to try to sort out the differences between different demands. So the thing with economics that's important to remember, it's not just about making money, but it's also, there's sort of a practical nature to that. There's a limit to how much money you can spend to clean up the water. And if you can't afford to clean it up, you might have to look for some other alternative. So, but all those come into play when it comes to water quality standards. And the water quality standards are published by the federal government and by state governments. In many cases, state governments can have stricter standards than the federal government. They just can't be less strict. And those standards are important because they determine the level to which, for example, a city has to clean up the drinking water before it sends it out to the residents. And it determines how clean the water that's discharged by a sewage treatment plant would have to be. So let's talk on this last slide about wastewater treatment. How do we do it? Well, the old school method was just what we call dilute and disperse. It was dump the polluted water in a place where hopefully it won't bother anybody. And by the time it gets to some place where people would be concerned, it'll be diluted and dispersed. This is an example of where Boston sent its sewage. You can see those one red dot's not very far out of Boston Harbor, so they made a new outfall that was farther out into Massachusetts Bay to help take that polluted water away from the coast. City of Chicago had a similar problem. They were dumping in the late 1800s their sewage into Lake Michigan, which also happens to be their source of drinking water. And as you might imagine, people were getting sick. And so what they did was they dug a canal called the Chicago Sanitary and Ship Canal, which connected the Chicago River to the Des Plaines River, which flows into the Illinois River. And once they did that, they started sending their sewage toward us. The idea was that as that moved downstream, the ecosystem would kind of take care of it, or at least it wouldn't end up in Lake Michigan. The first one's definitely true, or the second one is definitely true. It did not end up in Lake Michigan, but nature cleaning it up, if you put too much in, there's no way nature can keep up with that. So if you put a small amount of waste into the river, nature can dilute and disperse, and actually there's some microbes that might help clean it up. But if you put too much in there, then you just can't do that. And so we've gone to other options. We set up large-scale treatment facilities. This is an example of a sewage treatment facility for municipal sewage. So that's basically the sewage that you produce. And human waste is actually fairly easy to deal with. You basically screen out the things that shouldn't be going through the rest of the system. And then this system is set up to mimic what nature would do if you went to the bathroom in a nearby stream and it was just you. So the water flowing over rocks and things would bring a little air in. The bacteria can use that air and then can take advantage of the nutrients that you've added to the stream and basically break down whatever waste you put in the water. But when you have a city of thousands of people, or in the case of Chicago, millions of people, you need a better system than that. You kind of enhance what nature does. And essentially, this system is set up to encourage bacteria to grow and break down the waste. You end up with treated water, which can then be discharged to surface water, and sludge, which is the solid material, which is put into drying beds and then disposed of elsewhere. So that is a wastewater treatment system for municipal waste that's dominated by humans. If you had a factory, or if your city had a lot of factories in it, you would have to add something to this system, or maybe create a different system that addresses whatever waste is actually being produced. So that is what a large-scale system looks like. A small-scale system is something that you could have at your house. So if you live in the country, as I do, you need a septic tank. You need to treat your sewage. How does that work? Well, basically the same thing that the municipal treatment system was doing is what this does. The septic tank is a home for bacteria, and the bacteria break down the waste. The wastewater then goes into the drain field and percolates down into the soil. It has to be above the water table to work, because this area right here gives the bacteria another chance to go to work and break down the waste. The sludge over time builds up in the tank, and so every few years I have to have somebody come to my house take the lid off the septic tank. It's actually buried, so I have to dig it. And then we pull the lid off, and they stick a hose down there, suck up the sludge, and guess where they take that sludge? They take the sludge to a municipal treatment plant. And so then they run it back through this process, they dry the sludge out, and go from there. There are alternatives. This is a figure out of your book that shows some other things that can be done. It's got the sewage treatment plant there. You'll notice that they're using the wastewater to irrigate things. And that's just one example. Another thing you could do is reuse that water. The water coming out of a sewage treatment plant, not a septic tank, but a sewage treatment plant, is now required to be pretty clean before they discharge it into the river. And at that point, especially if you were using the river as a water supply, you would have to ask yourself, this water's pretty clean already. Can't we just clean it up a little bit more and reuse it? The one thing that prevents that from happening in most places is what's called the yuck factor. However, you don't get that option if you're on the space station. They do recycle all their water, they have to. And that's it. So I did go a little longer than I intended, but a lot of good, interesting information. One of the things that you need to find out for your term project is where your wastewater goes. Is it going to, is it going to one of these if you live out in the country, or is it going to one of these if you live in the city? You need to find that out.